This is Math 432, Applied Combinatorics. I'm Professor Asaph, and today we're going to be talking about trees in the graph theory sense. So what is a tree? A tree is a connected graph that contains no cycles. In particular, if it has no cycles, there cannot be a loop that would constitute a cycle from a vertex to itself, and there cannot be multiple edges between two vertices because those would constitute cycles. So it's in particular going to be a simple graph. But let's look at some examples, and let's think about the number of vertices. Let's say n equals 3 vertices. How many different trees can we think of? Well, let's just think of graphs on 3 vertices. There aren't that many. So, of course, we can have the complete graph. This looks like this. There's a cycle here, obviously, so this is not a tree. So this is a non-example. Now, we could take an edge away from this, and then what do we end up with? We end up with a graph that's connected still and has no cycles. So this, in fact, is a tree. And we can think about, okay, what if we took an edge away from this? Well, now we're kind of in trouble because it wouldn't be connected anymore, and this is it. This is the only tree on 3 vertices. What can we do if we had 4 vertices? So let's grab some vertices. Maybe we'll have a autumn tree for this example. And we're going to need some edges. We're going to need to connect some things. So let's think about having 4 vertices. So I could connect a vertex here, of course. And now what could I do beyond this? Well, I'm going to need some more trees, more branches. So I'm going to have a vertex here. But let's just add a bunch of branches first. Okay, now we'll stick a vertex on here. And of course, we're going to have leaves. A leaf is a vertex of a tree with degree 1. So this is a perfectly good example of a tree on 4 vertices. And you can see it doesn't matter how I orient it, right? I can make it like this. I can make it look like this. This is called the claw when we make it look like this. But this is a perfectly good tree. Well, let's get some more leaves, maybe have another autumn color, and say, well, what else could we do? Well, I could just start making a tree in a straight line. That's a pretty easy tree to make. So if we want to make a tree, instead of making it have a nice hinge point like this, we could just turn it into a straight line. See if my Lego Technics skills are up to snuff. So we can keep going here. That'll add us another vertex and one more vertex. And now we have 4. And we can see these trees are different, right? Because the connectivity of the trees is different. So I don't have a bijection from the orange to the yellow that respects the edge adjacency. That's what it means for trees to be different. If there's no bijection between them that respects edge adjacency. So these are my trees. Maybe I'll make sure they show up a little better and put them on a white background. These are the only 2 trees that I can have with 4 vertices. And you can figure that out pretty easily. If you think about this one, okay, well, this is the straight line tree. So if we don't have a straight line, right, then we're going to have a vertex of degree 3, right? So here's my vertex of degree 3, and now the rest of the tree is forced on me. So if I don't have a vertex of degree 3, I've got this, and if I do, then I've got that. So that's it for degree 2, for 4 vertices. So this is the example for n equals 4. And maybe let's do another example. What about when n equals 5? How many trees do I get? Well, I made these in advance just so I wouldn't have to futz with them. So we can have, apparently I didn't make them all fit. So we have the straight line tree. That's a fairly boring tree. We have the tree where there's 1 vertex of degree 3. And then we have this claw-like tree where we have a really high degree vertex. And then you can check that these are all the trees with 5 vertices. And now we can start looking at these trees and thinking about what properties they have. So remember, not a cycle. That's the definition of a tree. That's going to be an important characterization for trees. They do not contain cycles. So here is a small tree, and here are a bunch of bigger trees. Of course, we're going to try to count how many trees there are, but first let's look at some properties of the trees. One thing you might notice is that all 3 of these trees have the same number of edges, right? Here, I have my 5 vertices, and I always have 4 edges no matter how I've done it. And in fact, up here in this example, for both trees on 4 vertices, I have exactly 3 edges. And so you might start to wonder, is that a theorem? And in fact, I would say it's more of a proposition because it's not that hard to prove. So proposition, a tree with n vertices has n-1 edges. And here are our examples. Let's see how we could prove this. Trees lend themselves very nicely to proofs by induction. So proof we're going to do induction on n. So n is the number of our vertices, and let's do induction. So we're going to need a base case. The base case, the smallest tree is with one vertex. So what does a tree with one vertex look like? It looks like this, right? It's a single vertex with no edges. In fact, there are n minus 1 equals 0 edges. So there's 1 minus 1 equals 0 edges. Check. That works. We've done the base case. So now we get to assume our inductive hypothesis. So it's always a good idea to write it down. What does our inductive hypothesis say? That any tree with n minus 1 vertices has n minus 2 edges. That's my inductive hypothesis. So I'm going to get to use that as I proceed to prove my statement. Okay? Now, what I want to think about when I'm proving something by induction, what I want to think about is how I can go from the case that I have, which is n, down to the case where my inductive hypothesis applies, which is n minus 1. So how do I go from, for example, this tree down to one of these two trees? Well, you can just think about how would I reduce the number of vertices. So here, what I could do is I could take a vertex off. Well, which one could I take off? Well, if I take this guy off, well, then I have to kind of contract these guys in. That's just sort of confusing. But of course, I could just take off this piece, or I could just take off this piece. Now I've got a graph that has fewer. My inductive hypothesis applies, and then when I go to put this guy back on, I've just added one more edge and one more vertex. And that's sort of the crux of the argument. So let's leave that guy there. And let's think about how we can generalize that argument. So what we're going to do is we're going to assume that we have the case of n, the case of the theorem. So assume T has n vertices. Okay, let V be a leaf. A leaf, remember this is degree 1. How do I know a leaf exists? That's a great question. How do we know a leaf exists in a tree? Well, if we think about a tree, what's the definition? The definition of a tree is there's no cycle, okay? So if I start at any vertex and I just walk along my tree, eventually I have to get to a leaf. Otherwise, I would end up having to loop back because my tree is finite. I'm going to assume in this class all graphs are finite. So as I walk, right, I can't ever come back to where I was, otherwise I would have a cycle. So I'm never going to hit the same vertex again. So eventually I have to stop. And what does it mean to stop? It means you hit a degree 1 vertex. So I definitely have some vertex that's degree 1. It's called a leaf. So what I'm going to do is I'm going to think about T minus V. This has n minus 1 vertices, and it has n minus 2 edges. Because, we don't know that yet. It has one fewer edge. It has n minus 1 vertices. It has one fewer edge. And no cycles. So why does it have no cycles? Well, because when I take it off, clearly I'm not creating an extra cycle. I'm removing something. So I've taken off my vertex V, and now I've got just this guy left. So now I'm going to use my inductive hypothesis. So I know that by the inductive hypothesis, T minus V has n minus 2 edges. That's what my inductive hypothesis said. So I know that here, 3 edges, check. Okay, so what do I know? Well, remember we had this statement. T minus V has one fewer edge. Why? Because I had a degree 1 vertex. So now I'm going to add V back, adds one more edge. That implies that T has n minus 2 plus 1 equals n minus 1 edges. And that's the end of our proof. So once we take this guy and we add it back on, we've added one more edge and one more vertex. So now we're back up to n minus 1 edges, which is what we were trying to prove. So it is a fact that any tree has n minus 1 edges. We'll look at other properties of trees and equivalent characterizations of trees in the next video.